Welcome back to the 7th chapter of Multibody Dynamics using Alter HyperWorks, MotionView, MotionSolve. In this chapter, we will cover the concepts of redundant constraints, joint primitives, and motion function. When you are trying to build a model in Multibody Dynamics, it is always possible to over-specify the constraints in the model. In such scenarios, the system is said to be over-constrained. To make this concept more clear, I have tried to explain it using a mathematical equation in this slide. Consider a constraint equation, x minus y equal to 0. If we add the same equation, we get 2x minus 2y equal to 0. Clearly, you can see that this equation constrains the variables x and y identically to the first equation. Thus, the second equation is called a redundant equation. Now let's consider the example of a door to a frame with the hinges as shown in the figure. We all know that a rigid body has 6 degrees of freedom. Door, being a rigid body, has 6 degrees of freedom. Hinge represents a revolute joint in multibody dynamics. As I had explained in the previous chapter, a revolute joint constrains 3 translational degrees of freedom and 2 rotational degrees of freedom, totally constraining 5 degrees of freedom. This means that it only allows rotation about one particular axis. So if we consider that a door is fixed to the frame with the help of these 3 hinge joints, allowing the door to open and close, the total degree of freedom of this system will be 6, which is basically the degree of freedom of this rigid door, minus 5, and minus 5, which will give you a total of minus 9 degree of freedom. Hence, when the degree of freedom becomes negative, the system is said to contain redundant constraints. In this example, a couple of points is worth noting. They are: the hinge axis is required to be perfectly collinear. Otherwise, the door cannot be opened and closed. Only one hinge out of these 3 is actually necessary to perform this simulation in multibody dynamics, and the remaining 2 are redundant in nature. If such a system is introduced to MotionSolve, the solver will detect a redundancy in constraints and remove the equivalent of 2 hinges, or in this case the 2 revolute joints, from the model. Now, if you run the analysis, although the correct motion might get predicted, the effect of removing the 2 hinges from the solution process is that the reaction forces or torques will be 0, and they no longer contribute to the equations of motion. In reality, all the 3 hinges 1, 2, and 3 have reaction forces and torques. But say you want to request the reaction forces on hinges 1 and 2. If MotionSolve removes the first and the third joints as redundant, then you will not be able to recover the reaction forces or the torques at these locations, even though the motion prediction, that is the animation, may look right. It is very rare that a model requires or has some use of redundant constraints. So now, it is very rare that a model requires or has some use of the redundant constraints. So we now understand that these redundant constraints need to be removed. There are 3 different ways of removing the redundant constraints. They are: the first way is combining the degree of freedom with the lower pair joints or the joint primitives. I will explain about them in detail in the upcoming slides, making use of the compliant joints or the bushings. And the third way is to use flexible bodies in your model building process. This is a very effective approach, but of course at the expense of computation time. Now let us understand how the constraints are classified in MotionView. Constraints are basically subdivided into 5 different categories as shown in this slide. They are the lower pair constraints, joint primitives, or also called as JPrims, the higher pair constraints, motion, and other joints. Now let us understand the definition of each of these constraints in detail. The lower pair constraints. A lower pair constraint is an ideal joint that constrains contact between a point, line, or plane in the moving body to a corresponding point, line, or a plane in a fixed or another moving body. These have physical analogies, for example, a revolute joint. Joint primitives. The joint primitives constrain combination of individual degrees of freedom between the bodies. In most of the cases, there are no mechanical equivalents for joint primitives. Higher pair constraint. In higher pair constraints, the two bodies are in contact at a point or along a line, as in the case of ball bearing or disc cam and the follower. As in the case of a ball bearing or disc cam and follower, and the relative motions of the coincident points are not the same. A motion is a prescribed displacement, velocity, or acceleration on a body along a specific direction. When a motion is applied on the body, the free degrees of freedom of the body are replaced by the prescribed movement as specified by the motion, and thus motion is considered as a constraint. Other joints. This classification consists of constraints, which are used to specify algebraic equations, which are used to specify algebraic relations between two or more joints. So in total, there are 27 types of joints in MotionView. The flow chart on this slide illustrates the classification of constraints in MotionView. So under the lower pair constraints, we have the constant velocity joint, cylindrical joint, fixed joint, planar joint, revolute joint, screw joint, spherical or the ball joint, translational joint, and the universal joint. Under joint primitives or JPrims, we have at point, inline JPrim, in-plane JPrim, orientation JPrim, parallel axis and perpendicular axis JPrims. In higher pair constraints, we have point to curve joint, point to surface joint, curve to curve joint, curve to surface joint, surface to surface joint, point to deformable curve joint, and point to deformable surface joint. And we also have a constraint made joint. Under motion can only be applied either on a joint or motion can be applied using markers. And under others and under other constraints, we have couplers and gear. So these are the 27 types of joints that are there in MotionView to build the model. In the current and the next slides, I'll be explaining about the J primitives in detail. Joint primitives or JPrims don't have a direct physical analogy, but they have similar functions like the joints, basically to remove the translation and rotational degrees of freedom. JPrims are usually used to model more complicated mechanisms. They are often used in combination with other joints during the model building process, without introducing redundant constraints into the system. The table on this slide shows the different JPrims available in MotionView. They are at point, which is used to constrain 3 translational degrees of freedom, the inline constraint or the inline joint, which is used to constrain 2 translational degrees of freedom, the in-plane JPrim, which is used to constrain 1 translational degrees of freedom, and the orientation, parallel axis and perpendicular axis constraints are used to constrain 3, 2 and 1 rotational degrees of freedom respectively. In this slide, I will explain one of the popular JPrims, that is the in-plane JPrim, in detail. This is a constraint primitive that requires that the origin of the reference marker on body 1 in the figure which is shown in this slide to stay in the XY plane, defined by the origin of the J reference marker and its Z axis. The in-plane primitive constrains 1 translation degrees of freedom. It restricts the translation along the Z axis of the reference marker J on body 2. However, all the rotations are allowed. One of the most important application of this in-plane JPrim is the 2 or 4 post-test rig for the suspension system. In this slide, I will be explaining briefly about the motion function, since it will be used in the demo exercise for chapter 7. Generally, there is a function to measure the force and or torque in every type of entity in MotionSolve that produces a force or a torque. For example, we have a bush function to measure the force or torque produced by the bushing entity. We have a joint function to measure the force or a torque produced by the joint entity. And similarly, we have the motion function to measure the force or the torque produced by the motion entity. The syntax for the motion function is motion followed by its arguments, which are id, jflag, component, and the reference marker. So the id of the motion joint or the motion marker, so the id represents the id of the motion joint or the motion marker element. The j flag is basically equal to 0 or 1. It means that the forces and the moments are reported at I or j marker respectively. So if you give 0 here, then the forces and the moments are reported at the I marker, and if you give 1 here, then the forces and the moments will be reported at the j marker. And the third argument is basically the component. If you have 1, it returns the force magnitude. If you have 2, it will be returning the value of the force x component. 3 will return the force's y component. 4 will return the force's z component. 5 will return the torque magnitude. 6 will return the x component of the torque. 7 will return the y component of the torque. And 8 will return the z component of the torque. And Rm in this argument, it refers to the reference frame in which the components are reported. So if you have Rm is equal to 0, then it implies a global reference frame. Now I will be giving a demo on the exercise 7. Thank you.